Hello and welcome to the fourth installment in my 6809 Playground Homebrew Computer Series. Today I'm going to talk about address decoding and some of the other signals that are needed to access memory devices. If you've been following along, it's really great to have you back. But if you're not familiar with the background of this project, I put a link to the introduction in the description below. So the address decoder has a pretty important job, and that's to look at the address that the CPU puts out on the address bus and to figure out which device, like a RAM chip or a UART or whatever, is the target of the bus transaction, and then to let that device know by asserting its chip select input. This is accomplished using a series of logic gates to match the address bit patterns associated with each chip select. And those logic gates might be inside a discrete logic IC like, a 7400 quad NAND chip, or they might be inside a chip with a higher level function like the 74138 3-to-8 decoder. Now, obviously, because I'm going to be building a circuit to match address bit patterns, I will need to decide how the address space on the system will be laid out so that I'll know what those patterns will be. The 6809 has a 64 kilobyte address space. In that address space, we have to put RAM, ROM, and the I/O devices. There's also some details that are specific to the 6809 that we need to pay attention to. First of all, the reset and interrupt vectors are placed at the very top of the address space, meaning that the decoder needs to select the ROM where those vectors are located when the vector is being fetched. Now, typically this is handled by simply, mapping that ROM at that location. Now, I'm going to be doing a little foreshadowing here. There's some additional CPU signals that I can actually use to tell when a vector fetch is happening, so it is possible with some additional logic to put the vectors anywhere and even to change what that location is based on what vector is being fetched. But for now, I'm just going to go with the simple method of putting the ROM at the top of the address space. Second of all, after a reset, the 6809 assumes that there is something, typically RAM, starting at address 0. And that's because the DP or direct page register defaults to 0 after a reset. This is for compatibility with the 6800's direct page, which is really the same thing as the 0 page on the 6502. Now, while it's possible to change the direct page location on the 6809 by modifying the DP register, it's probably best if I go ahead and just, map at least some RAM there. Now, other than those two constraints, I'm free to, put stuff basically anywhere. So with that in mind, let's talk about the Playground's memory map. I designed this memory map with a few specific system goals in mind. First, the system should support relatively large amounts of RAM and ROM through the use of banking. Second, there should be fixed ROM and RAM regions for critical operating system functions that are always accessible, no matter what other RAM and ROM banks are currently selected. Third, the banked RAM regions should be flexible. So, for example, a program might have a small code size that could fit into 8 kilobytes of RAM, but maybe it operates on a large data set that can benefit from having large bankable regions available. Alternatively, a program might have a relatively large code footprint, perhaps even in excess of 64 kilobyte, but operate on a comparatively small data set. Maybe something like a handful of state variables in a command buffer or, game levels or something like that. And finally, decoding for I/O devices should be regular and minimize the amount of additional decoding logic that peripherals have to do themselves. And then also to allow for quite a lot of future expansion and experimentation. So based on those goals, I defined 6 basic regions. A low banked RAM region, where some amount of RAM, I haven't really decided exactly how much yet, can be banked in 32 kilobytes at a time. A fixed RAM region, where 7.5 kilobytes of RAM is available for use by the operating system. A 512-byte I/O region that's comprised of 16 individual 32-byte device regions. A high banked RAM region, where some amount of RAM, again to be determined later, can be banked in 8 kilobytes at a time. A banked ROM region where anywhere between 128 kilobyte and 512 kilobyte flash ROM can be banked in 8 kilobytes at a time. And an 8 kilobyte fixed ROM region that will contain the base operating system routines, the monitor program, and the vectors. Okay, so as you can see, I've also included the address bits that encode for each region. So the low banked RAM is trivial to decode. I can just use the A15 signal directly as the active low chip select for the SRAM chip there. The high banked RAM, banked ROM, and fixed ROM regions are also relatively simple to decode. I can choose a 74138 3-to-8 decoder IC. It could easily handle this task. The fixed RAM and IO space regions, however, are a little more complicated, and I still have to deal with the individual IO selects that are within the IO space region. Okay, so before I dive into designing the decoder, I want to say a few words about timing. So as I discussed in the clock generator installment, the information required to perform address decoding is guaranteed to be valid on the rising edge of the Q clock. I described it that way because Q is the signal that you're going to use if you need to latch the address for some reason. But the address bus and the other related signals are actually valid just a little bit before Q goes high. So the upshot of this is that if you're not latching the address and just using combinatorial logic, you get a little bit of a head start. Now, on a read cycle that's issued by a 6809 running at 2 megahertz, from the moment this information becomes stable, we have roughly 330 nanoseconds until the data has to be valid and the data bus stable in order to meet the 6809 setup time. Now, if we're going to try running a 6309 at 4 megahertz, we only have 165 nanoseconds. Now, consider the AT28C64 EEPROM, like the one I'm going to be using for the fixed ROM. Those actually have an access time of 150 nanoseconds typically, which means there's not a lot of time to assert this chip select signal. I could give the EEPROM a bit more time by building the MRD clock stretching circuit that I briefly mentioned in the clock generator installment, but I want to avoid that if I can. I prefer to have predictable instruction timings, and so it's pretty clear that I'm going to need to pay careful attention to the propagation delay of the decoding circuitry. Now, I also will be buffering the CPU's address and data buses with 74 AHCT-245 bus transceivers, which themselves have a typical delay propagation of 9.5 nanoseconds. There's actually a good reason to do this though. Not only does it overcome the 6809's relatively low fan-out capability, but it also effectively converts the TTL logic level outputs on the 6809 to 5-volt CMOS logic level outputs, which means that I have a wider selection of components available for use in the rest of the system. Specifically, it allows me to use 74 AHC series logic ICs, which are typically faster than 74LS chips and consume a lot less power. So because of this base propagation delay of 9.5 nanoseconds, I need to avoid having multiple stages in my address decoder, where the later stages rely on the result of some other prior stage, because having those would cause those propagation delays to kind of stack up. Now, I started putting together a decoder design using standard 7400 series logic ICs. The 74AHC138 decoder is fast enough, but complete decoding required several additional logic gates, especially for the fixed RAM, plus an additional stage of the 74AHC138s and some address line inverters were required to decode the IO space region. The result, of course, was that both the decoding time and the chip count were ballooning. So because I've already used a GAL 22V10 in the Playgrounds design, I figured it couldn't really hurt to see what it would be like to use it for the address decoder. So first, let's take a look at the two regions that are the most complex to decode, the fixed RAM and the IO space. In the fixed RAM case, I can't just look at the 3 upper bits, because the last 512 bytes of that 8 kilobyte region are taken up by the IO space. So the decoder has to match on several bit patterns depending on how far into the fixed RAM region that's is being accessed. Now, if this problem looks familiar, it's because it's very similar to the clock selector logic that I discussed in the clock generator video. This is easily expressed as a sum of products in the GAL logic description language. Next, note how A9 through A15 have to be examined to select the IO region, and then A5 through A8 have to be examined to select an individual device. That's 11 total bits. Now, happily, that fits neatly into a 22V10, which has 12 dedicated input pins, and with 10 output pins, the 16 total IO selects could be split evenly between 2 GAL chips, which leaves 2 outputs available on each. So, as for the 5 regions that aren't IO space, recall that the low banked RAM doesn't need any decoding help at all, because A15 can be used as the chip select directly, which leaves 4 regions that need to be handled, 2 RAM regions and 2 ROM regions. And since we have 2 spare outputs on each GAL after decoding the IO space, this fits perfectly. Here are the equations for the first decoder chip. The equations for the IO device selects are very simple. Each individual IO select output just needs to match a single bit pattern. There is no need to match the IO space region separately and then decode each subregion. The GAL has plenty of room in the AND gate fabric to match the IO space prefix in each equation. The equations for banked ROM and the fixed ROM are also very straightforward. They only have to match 3 bits each. Now here are the equations for the second decoder chip. The I/O device selects in this instance are nearly identical to the first, except for the bank bit is a 1 rather than a 0. Now the fixed RAM equation here, what it does is it just sums the 4 different products to produce the FRAM select signal. And then the high banked RAM is very similar to the simple decoding of the 2 ROM regions, only needing to match 3 bits. So there you are with a complete address decoding solution and just 2 24-pin chips, with a low and uniform propagation delay no matter what address is being decoded. Okay, so we have another building block, but we're not quite done yet. We can decode addresses and select devices, but there's still the task of actually reading the data from or writing the data to the selected device. So let's take a look at what's necessary to do that. First, let's take a look at the 6551 asynchronous communications interface adapter. This is a UART made by the Western Design Center and is designed to interface with the 6502, which uses the same bus interface as the 6800 and 6809. The datasheet just uses slightly different chip names for the read, write, and clock signals. Now taking a look at the other side of the package, we see the chip select inputs, plural. CS0 is an active high chip select, and CS1B or CS1 bar is an active low chip select input, and both need to be asserted in order for the device to be selected. CS1 bar is what we need to connect to one of the address decoder outputs. But what about CS0? Well, CS0 is there to provide some additional address decoding flexibility. If you only have a single ACIA device, you can just connect this to 5 volts and forget about it. But let's say you have a dual RS-232 interface card with 2 ACIA chips that fits into a computer's expansion slot. And let's say that expansion slot has a single chip select line and then 4 address lines representing the 4 least significant bits of the address, A0 through A3. Well, how are you supposed to access the second ACIA? Well, the answer is that you use one of the address lines, let's say A2 in this example, since the ACIA has 4 registers. An inverted copy of A2 is connected to CS0 on the first ACIA and then directly to CS0 on the second ACIA. Now, there are a few ways to invert A2 that could be used in this hypothetical interface card, but we're not going to worry about that for now. This design pattern, what it does is it allows secondary address decoding to happen, kind of in parallel with the primary address decoding that asserts CS1 bar. If there were only a single active low chip select input on the ACIA, then the secondary decode to differentiate between the 2 individual chips would have to happen after the primary decode, which could cause those propagation delays to stack up. Anyway, that's just some additional context to keep in mind, just for a little later. The important takeaway here is that the peripherals with the synchronous bus interface, like this one, that are specifically designed to connect to 6502 or 6800, are trivial to deal with. Now let's look at the microchip SST39SF010, which is the 128 kilobyte version of the flash ROM chip that I plan to use for the banked ROM. Here's the chip select input called chip enable, but instead of a clock input and a read-write input, we have an output enable input and a write enable input. This chip has an asynchronous interface that expects a strobe on the input corresponding to the type of transaction, a read or a write, that's being performed. The AT28C64E PROM that'll be used for the fixed ROM, and the SRAM chips that'll be used in the various banked RAM regions of the machine, they have the same requirements. So I'm going to need to add some logic to generate these strobe signals. So let's go back to the ever so handy 74138 3-to-8 decoder. Just as a reminder, this chip takes a 3-bit binary number as an input and asserts a single corresponding active low output. We can use one of these to generate the read and the write strobes. Let's take a look in Logisim to see how this can be done. So what I've done here is connect the RW input to the first input bit, the 1 position, and the E clock signal to the second input bit, the 2 position. The third input, the 4 position, is just tied to ground, and the enable inputs are just connected so the output is always enabled. Then I've connected the write strobe output to the Y2 output and the read strobe output to the Y3 output. So recall that the RW signal is high for a read and low for a write. Now first let's consider the output when the E clock input is low, which will be the case when the RW signal transitions to the value that will be used for the bus transaction. The input value is a 0 if RW is low for a write and 1 if RW is high for a read. That means Y2 and Y3 remain high or deasserted, and since nothing is connected to the Y0 or Y1 outputs, nothing happens. Now consider the output when the E clock input goes high. If RW is high for a read, then the input value would be 3, and the read strobe will go low. If RW is low for a write, however, then the input value will be 2, and the write strobe will go low. Finally, at the falling edge of E, the input value will become less than 2 again, and whichever strobe output was asserted will become deasserted. So that will work to generate our read and write strobes, but I want to think a little bit more about the flash ROM, specifically the write enable signal. I want to be able to reprogram the flash ROM in system, but I don't think I want to be able to reprogram it accidentally. I kind of want to have an explicit write enable for the flash ROM, which is something that I should be able to control with a register that will be used to bank the ROM. After all, with a 512 kilobyte flash ROM, there will only be a total of 64 banks, and that will leave bits available in that register for a flash write enable bit. I want this flash write enable bit to be able to gate the write strobe on the flash ROM, and so there are a couple of obvious ways that we can do this. So the first option is to simply add a second 74138 to decode the flash write strobe separately. In this case, the flash write enable signal would be connected to the active high enable input of the 74138, which then has the effect of gating the flash write strobe. As you can see, despite E being high and the read write being low, the flash write strobe is still deasserted because the flash write enable signal is low. But if the flash write enable signal were to go high, then the flash write strobe would assert along with the standard write strobe. Now the second option is to use a couple of NAND gates, one to invert the standard write strobe and the other to mix it in with the flash write enable signal to generate the flash write strobe. When the flash write enable signal is low, the flash write strobe is deasserted, but when the flash write enable signal is high, the flash write strobe will be asserted at roughly the same time as the standard write strobe. The disadvantage this has over the first option is that there's propagation delay added by the NAND gates. Okay, so for each of these two different options, we only need to add one more chip to provide a separate flash write strobe. That's not too bad. But is there anything else that we want to do? Let's go back to the 6551 ACIA and its two chip select inputs, and what I said earlier about how we can get some additional address decoding flexibility if we're willing to fiddle with, or more specifically invert, some of the address lines on a per device basis. I already know that I want to have more than one serial port on the playground, and I already know that I'm going to need more than one 6521 PIA to control RAM and ROM banking. Now, I'd like to group devices with similar functions together and minimize the number of I/O device selects used by devices that are present on the main board if possible. Well, rather than inverting individual address lines on a device-by-device basis, maybe the memory interface could provide inverted copies of the 5 least significant bits of the address bus for any device to use for this purpose. I could do that with just a single 7404 hex inverter IC. Now we have a 3-chip memory interface, a 74138 to generate the read and write strobes, a 7404 to generate those inverted copies of A0 through A4, and either a 7400 or another 74138 to deal with the flash write strobe. But I know what you guys are thinking. That's 3 chips, and this guy's going to use another gal, isn't he? And the answer is yes, I am. And I think it's perfectly justified because I actually want to be replacing 4 ICs with this solution here. Recall that the address and data buses are going to be buffered to overcome the low fan out of the 6809. Well, I want to give the same treatment to the RW output on the CPU, and all the current bus transceiver inputs are already accounted for. So here's what this looks like. Here are the pin names, and note that I'm using 6502 style names for the clock input and read-write signal here, because this module would actually work perfectly well on a 6502 system, so I figured I might as well make it more approachable. Now, these two equations generate the read and write strobes. RD is asserted when the clock output is high and the read-write signal is high, and WR is asserted when the clock is high and the read-write signal is low. Now note these outputs were declared as active low above. Now this equation, it simply mirrors the read-write signal to an output pin named RWO for read-write output, effectively using the GAL as a buffer. Now the next equation generates the flash write strobe. It's identical to the standard write strobe except that it also considers the flash write enable input. And finally, these equations provide inverted copies of A0 through A4 on outputs named NA0 through NA4, which can be used with the additional chip select inputs on the various peripheral chips in order to more efficiently use the individual I/O device subregions. And so here's the updated diagram showing the memory interface and its sort of relative place in the general scheme of things. So here's the portion of the schematic that deals with the CPU and memory interface. There's a chip on there that I've dimmed out because I haven't talked about it yet, but that's coming in a future episode after we have some real code running on the hardware. In the meantime, just pretend that the chip enable inputs on the address bus buffers are connected to ground. Now, note that the address outputs from the CPU are labeled DA0 through DA15. The D stands for direct connection. And these signals are used only in the memory interface portion of the circuit. And here's the address decoder schematic. I know it's not terribly exciting since it's just two chips and all the action is really inside the gals. But I did want to point out that the address decoder takes the output of the address buffers and not the signals directly out of the 6809. This will actually become important later, specifically when I talk about that dimmed out chip from the previous diagram. Okay, so I think I'm going to wrap this episode up here. Before I build up the decoder and memory interface on breadboards, I want to have the RAM and ROM modules built, and so that's what I'm going to cover in the next installment. Thanks for watching, and I hope to see you again soon.